So today I'm going to talk about what we do at the Samsung Audio Labs and how we use the simulations. First, just a quick introduction to Samsung Electronics and to our Audio Lab in just north of Los Angeles. Then I will have two examples. One is a time-dependent electromagnetics study of nonlinear distortion in loudspeaker transducers. And the other one is an optimization study of a waveguide that's just a pure acoustics problem. And then at the end, I have a short conclusion and outlook. Samsung Electronics was founded in 1969 in Korea. The vision for 2020, as it's stated right now, is that Samsung Electronics is committed to inspiring the world and creating the future through innovative technologies, products, and design that enrich people's lives and contribute to social prosperity. So that's a big backpack we carry around with us all day, every day. And I do that with about 320,000 other employees of Samsung Electronics. On this picture, you see the digital city in Suwon, South Korea, where about 35,000 people work in these buildings. Samsung is really committed to that vision of 2020, and for that, there's 35 research and development centers around the world. About 1/5 of the entire workforce of Samsung Electronics works in research and development, and also the dollars amount that Samsung spends on research and development are pretty impressive. So every day, they spend almost $41 million on research and development. So that's a yearly budget of almost $15 billion in research and development, which is huge. I want to point out one specific research center. That's the red dot up there. That's where I work. It's called Samsung Research America, and it's headquartered in Mountain View in the Bay Area near San Francisco, and our office is just north of Los Angeles. So there's a couple satellite offices, but we all work with Mountain View. All right, and the results from this investment in R&D produce results. So we can see that in the patents. The last 4 years, Samsung was number 2 for issued patents, number of issued patents in the US. And also in Europe, in the last 4 years, it was always in the top 3 companies for number of issued patents. I should say the numbers for 2015 and 2014, I couldn't find the number of issued patents on the web. I searched the European Patent Office's all the possible ways I could, but those are the applied patents. So for 2015 and 2014, there's a little asterisk. Those are applied patents. So focusing further down to our audio lab, we are in Valencia, California, about a 45-minute drive north of Los Angeles. And the audio lab started in 2013 when Samsung decided that in order to augment their best-in-class picture quality, they needed to keep up with the audio quality as well, which is not an easy task if the TV gets smaller and smaller to make the sound better and better. But our first hire, my boss was able to have a sandbox of 1,700 square meters and basically built what he wanted in there. So that was, I think he was pretty happy. We built 2 anechoic chambers that you can see. Let me see the laser. This anechoic chamber here is a standard anechoic chamber. We call it a 4-pi chamber because all 6 walls are covered in these sound-absorbing wedges where we do anechoic measurements. And then the second anechoic chamber here is a very specialized anechoic chamber. The people that built this, they said that they've never built anything like it. And it's an anechoic chamber where one side, here we have a door that opens, and on that wall there is no absorbing wedges. So it's a solid wall, a reflective wall. And we use that to mainly measure our TVs and soundbars as they're either wall-mounted or placed near a wall, so to simulate those conditions. Then we also have 3 listening rooms, standard listening rooms to do critical listening, blind listening tests. And one neat feature down here, it's hard to see, but there's a hole in the wall here that contains a cube that can rotate. So we can have 4 TVs on this cube behind, and usually we put it behind a screen. We do blind listening to get better results in our listening tests. And that cube can rotate. So within a couple of seconds, we rotate from one TV to the other, and we go through our listening tests. So it's pretty fun. But I think our biggest asset is our team. We have 21 full-time employees with over 300 years of research and development experience in audio engineering. 4 of those are PhDs and 6 masters, and also 8 of us are active musicians. So we all have a passion for music, and if you look at the names on the sides there, those are some of the places where people worked before coming to the Samsung Audio Lab. Then in 2015, we brought our first product to market that we designed at the Samsung Audio Lab. It's the R-Series wireless speaker. We used very simple, at the time, COMSOL simulations, because I had just started and nobody else was doing simulations. Simple simulations for the tweeter phase plug to calculate how the sound diffracts around this little piece here at the top of these 2 loudspeakers. And then we also used electrostatic simulations to calculate the woofer, which is the thing producing the lower frequencies here. Inside is a speaker that produces the lower frequencies, and we did some electromagnetic simulations for that driver. In 2016, this is not a product I want to highlight. In November of 2015, we heard about this project that Samsung wanted us to do, and that's a soundbar that can play Dolby Atmos sound or any 3D sound, basically. And it should have 2 upfiring drivers here that project sound to the ceiling and down to the listener to generate an enveloping sound, or like a 3D sound. And as I said, it was in November 2015, and we had to show a prototype in January 2016 at CES, a working prototype. So without simulations, this was almost an impossible task, and I did simulations for the Waveguide on this product for the channels firing up towards the ceiling, making sure the sound is directed towards the point where we want it to. All right, that's for the introduction. Now let's get a little bit into a little physics. For those of you who don't know, this is a quick introduction to loudspeaker technology. Usually we have an enclosure with a transducer sitting inside. Here's a cut. And I took these pictures from the COMSOL documentation, so it was really nice that I could just use it straight out of COMSOL. And then let's start here. The enclosure has a baffle, is what we call the front surface, and that's depicted here in white. And then we have suspension elements. So there's an outer surround and an inner spider. Those are suspension elements holding the entire thing in place. Then we have a diaphragm, which is moving up and down, and you can call it a dust cap or a center cap that's pushing air, creating the acoustic waves. That diaphragm is attached to a former, and on that former there's a voice coil. So there's a certain number of turns of a coil on there, and that coil sits in an electromagnetic gap here that's been driven by this magnet, a ring magnet, and the pole piece that's guiding the magnetic field through that gap. So there's a lot of nonlinearities that can happen in a loudspeaker, and as you will see later, nonlinear effects can be detrimental to a loudspeaker or the sound quality of a loudspeaker. So there's in the AC/DC domain, we have nonlinear magnets. We have saturation of steel, where the B field is just so high that it saturates the steel. In structural mechanics, we can have anisotropic materials to large deformations, and also frequency-dependent damping. In the acoustics, this is where multiscale comes in. So we work from 20 hertz to 20 kilohertz, the audible audio range for a human, which means we have wavelengths from 17 meters to 17 millimeters. And if you want to get really fancy, there can also be heat transfer problems in loudspeakers. And fluid dynamics, for example, this port here has air flowing in and out, so there can be turbulence, all sources contributing to nonlinearities. All right, why is nonlinearity such a big problem? And then this is going to be fun, because I get to play first an ideal woofer. Okay, so that sounded pretty good, I hope. And if we have a nonlinear woofer, we created one that was pretty bad and has strong nonlinearities just for the purpose of the demo. It sounds like something you don't really want to buy, right? You don't want to waste money on this. Luckily, there's some smart people that work in controls, and they can use lump parameter models to counteract these nonlinear distortion. You can see the lump parameter model up there, and I'm not going to get into details, but what we need to feed these lump parameter models are these kinds of curves that you see over here. So we have a stiffness curve here, and at the bottom we have the voice coil excursion. So as that voice coil moves in and out of the gap, the stiffness rises. The spider and the surround kind of get stretched to the point where they're stretched all the way and then get really stiff. We also have a force factor, so the amount of B field that the voice coil sees is maximized at the center, and then as you move out of the gap, that B field drops off. And then also there's inductive effects that vary with the voice coil position. And so if we can measure these curves in equipment and do some system identification to get these curves, and I want to show you how we can get those with simulations as well. So I built a COMSOL app that's on our server for our transducer engineers that design these transducers day in and day out so that it can get these curves really quick. So this is a simulation tool for the stiffness where we import a geometry, we assign the selections, and today I just learned in a mini course there's some ways that we can probably optimize this already. So I already learned something today to make this app better. We assign materials properties, we can mesh it, and then we solve it for an outstroke and for an in-stroke. We assign a displacement and calculate the force that's required for the displacement, and we get the stiffness curves here divided into the stiffness of the surround, the stiffness of the spider, and then the total stiffness is just a combination of the two. Similar for the BL, the force factor that's acting on the voice coil. There's an app, again, we import a geometry, assign materials here, you can see define the selections, assign materials, and here you can see we use nonlinear steel. Here, this is the saturation curve of steel for the steel 1008. Then we mesh it, and we can calculate the B field in this transducer. And from this B field curve, which is the strength of the magnetic field here in the gap, we can integrate over it and get the BL curve. We can also look at saturation, which is something that's really hard to do experimentally, if not impossible. We can look inside and see, okay, do we have saturation in steel at certain points? And we can look at, okay, what is the operating point of a magnet? Do we utilize the magnet to the maximum efficiency? All right. Now, inductance is a little bit of a tricky beast because it's time-dependent phenomenon. As you can see here, the inductance is coupled to the change in current or the change of flux inside the loop. And I'm not going to explain all these equations. That will go too far today. But what I want to point out is that we have flux here that's basically the integral of the B field inside the wire loop. Excuse me. But the B field is linked through the Ampere's law to the current density. And the current in the voice coil is driven by the input signal here. Then the velocity, this is kind of like a Lentz term, and here the inductive term. So they all play together, and we need to couple this. So it's a really strongly coupled problem. And so for that, I set up a time-dependent simulation where I coupled electromagnetics with a lumped parameter model for the mechanics. So we have a nonlinear spring and damping here, and a given mass of the diaphragm and the suspension, and we solve the electromagnetics with finite elements. So because we have large deformations, my first approach was to use a moving mesh, and there's actually a nice tutorial on COMSOL on how to do this, which I found 2 years after I had to model this. So this was 2 years ago. And then I found a tutorial, and I was like, oh, that's nice. Somebody put it in a nice form and explained how to do it. But there's actually a smarter way of doing this in COMSOL, and that's by using the fact that the voice coil is really thin, so we can define current on a thin line here, and then apply a window over which that current is actually flowing. So that window can move up and down. In COMSOL, you can see here, I defined a current that has this function here, piecewise 1 of z minus u. So z is the spatial coordinate in vertical direction, and u is the displacement that we get from the lump parameter ordinary differential equation. And with that, we were able to simulate it quite a bit faster, actually. Probably we saved a factor of 2 to 3 in computation time by doing moving physics instead of moving mesh. And as you can see here, this transducer here has some interesting effects, and let me explain real quick. At the top here, this red curve is the static BL curve. So if we just leave the driver alone and move the voice coil bit by bit and calculate how strong is that force factor, then we get the red curve. Now, on top of that, we have those inductive effects, and you can see how the instantaneous BL value is jumping around that red curve. It's not really following the static curve. And that's one source of distortion that I'm going to show. Then transducers engineers that are here in the room probably know, well, we can use shorting rings that kind of is 2 squares here that absorb the induced currents and don't affect the B field as much. And you can say if we do that, then we get an instantaneous BL value that's a lot closer to the static curve. So in the control, in trying to using nonlinear control, we're actually a lot closer to the truth in this case than what we were before. All right, and here's just a comparison, and you can imagine that the driver on the left probably doesn't sound as good as the driver on the right. All right, that was the first example. Next example. I need to hurry up a little bit. Samsung has developed these giant LED TVs that are now for sale, and you can buy them for your living room if you have deep pockets. And they look great. But we were tasked with developing an audio solution for this case where they wanted the loudspeaker to be really shallow and fit right next to the TV. The technology for the TV comes from LED cinema, and actually if you go to Zurich, there's one of worldwide of 4 LED cinemas in Zurich that you can go and check out. And the audio requirements are pretty stringent. We need a very wide sweet spot, so we need to cover a wide audience, and we need to cover also an audience that's close and far away. So there's a vertical control that we need to have as well, acoustically. And they must be able to play at really high volumes. Traditional cinema loudspeakers look something like this, and they're placed behind a porous screen. And you can see the really big waveguides that take up a lot of space to control the sound field. This one is a little bit smaller, but it's probably also less loud, if I can say that. So quickly, what is good sound quality? And you might know that if a loudspeaker has a flat frequency response, then the sound quality is good. It sounds really nice to your ears. But if you measure a loudspeaker without any type of equalization, it probably looks something like this. Hopefully not this bad, but this is just as an example. So we can use equalization to optimize the transfer function to a specific point. Here we optimize it for the best seats in the house in the center. Now, what you need to know is that at low frequencies, the loudspeakers behave pretty much like a light bulb. They shine, or they direct sound in all directions at low frequencies due to diffraction. And at higher frequencies, they behave more like a light bulb, so they shine more towards a small spot. So it's not really possible to have this optimal sound in every seat. And if you're sitting off axis at a certain degree, then you don't get a flat frequency response. You get something more that looks like bumpy like that. And if you look at it in the directivity plot, this is a bad example, but I want to show that it's hard to get good frequency response off axis. So what you can try to do is to smooth out these bumps here and get a straight line for the off-axis curves instead of these bumpy lines. So I set up an optimization example. I don't want to get into too much detail about what the parameters were, because I'm really tight on time here, and it's probably not as interesting. But this was the target. So we said at a 60-degree off-axis, we have a target curve with a 6 dB down point at 10 kilohertz for 60 degrees off-axis. That means the beam field is, the beam width is 120 degrees horizontal. And then we added another extra line in here, but we didn't really know how steep to make those lines. So we added the slope of these lines as additional optimization variables. So this is probably what's more interesting for you guys. We used LifeLink to COMSOL, to SolidWorks. And then we used just a simple pressure acoustics module with, where we assigned a constant acceleration down here at the throat where a driver is producing the sound. And also we made good use of symmetry, assumed that this loudspeaker is built into a wall, so we used 2 pi conditions. And there's some other interesting facts here if you want to read. And this is how the optimization performed. And you can see that the objective here, getting close to those straight lines, is converging pretty fast and then kind of starts dancing around. That's the feature of the parameter optimization with gradient-free solvers that we used in this case. And it's just kind of tweaking little bits and to really trying to get this black line here and this red line to match up with the targets. Okay. Well, we ended up with the final geometry, and we took that geometry straight from COMSOL and put it in a 3D printed waveguide, and then we tested it in our 2 pi chamber. And here are the results. There's a really good match between simulation and experiment. As you can see, the straight lines, or the solid lines, are simulation, and the dashed lines are the measurement in the chamber. And also you can see the target curves again. So we have one horizontal plane, and in the vertical plane, both ways match pretty well. And also in the directivity plots, simulated and measured response are very similar, and in the vertical plane as well. All right, that was the second example. These are a few small simulations that we're working on and we're interested in, and hopefully I can learn enough here at the course, the mini courses, to actually get a good implementation of the both. One is topology optimization for acoustics. You see an example here. I actually presented this last week in New York. And the other one will be turbulence in ports. So here we have a straight port that produces a lot of turbulence, and this is a flanged port that seems to work better. But these results are not very physical. I didn't do any verification. I'm not sure what you see here is actually what would happen in reality. So in conclusion, I hope you now know that loudspeakers are inherently multiphysics and nonlinear. And I want to point out one point down here. Simulations always need empirical backup. So if you're in here and you're more like a hardware person or working in other areas than simulations, you're not going to go out of business just because we have COMSOL. We still need people doing experimental work for us. And also, do not hesitate to connect with COMSOL support. They're really helpful in a lot of cases. I want to thank Zoran and Aliona for bringing me here to Lausanne. I want to thank the COMSOL support team, the COMSOL team in Los Angeles, and my team in California. Thank you very much.